It was discovered by Galileo and refined by Isaac Newton. It was one of the deepest mysteries in all of physics. In a vacuum, and only in a vacuum, all bodies fall with the same constant acceleration. For all of us, the effect of the Earth's gravity was probably our first encounter with the laws of nature. And whether or not we understand how gravity works, we have an innate fear of what it does. But exactly what is the effect of gravity? From common experience, we do know one thing about the rate of a falling body. The speed of a falling body increases as it falls, which means that it accelerates, dropping faster and faster as it falls. Some bodies fall to the earth quickly and directly, while others behave quite differently. In some cases, the pull of gravity can be resisted almost indefinitely. To make any sense at all about how and why bodies fall, we need to separate the effect of gravity on a falling body from the opposing effect of the air through which the body is falling. In other words, we have to imagine a body falling, not through the air, but through a vacuum. For instance, what happens if a penny and feather drop simultaneously from the same height? They behave exactly as we'd expect, each falling at a very different rate than the other. But that's only because of the effect of air resistance on the two objects. In a vacuum, and only in a vacuum, a penny, a feather, and any other object will fall at exactly the same acceleration. With virtually no air remaining inside the glass tube, the penny and feather are now in a vacuum. When the penny and feather are released, we'll witness the law of falling bodies in action. Without the effect of air resistance, in other words, in a vacuum, all bodies, regardless of their weight, will fall at exactly the same acceleration. When Apollo 15 astronaut David Scott explored the airless surface of the moon, he couldn't resist repeating this classic experiment for all the world to see.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Mr. Galileo was correct. Nearly 400 years ago, at a time when all the world believed that heavy bodies fall faster than lighter ones, Galileo realized that in a vacuum, all bodies would fall at the same acceleration. Galileo couldn't produce a vacuum, but he could imagine one. He pictured a heavy body attached to a lighter one. Would this compound body, he asked, fall faster or slower than the heavy body alone? If the lighter body did fall more slowly, it should slow down the heavy body, so the compound body should fall more slowly than the heavy body alone. But the compound body is actually heavier than the heavy body alone. Therefore, the compound body should fall faster than the heavy body, not slower. Obviously, the long-held view that the heavier a body is, the faster it falls, leads to an inescapable contradiction. Galileo realized that the only logically acceptable view was that all bodies, regardless of their weight, fall at exactly the same acceleration once the effect of air resistance is removed. If all bodies in a vacuum fall at the same acceleration, the next question is, exactly what is that acceleration? Earlier theories of accelerated motion held that a body would fall greater distances in later intervals of time, and that those distances would follow the integers. That is, 1 unit of distance in the first time interval, 2 units of distance in the second time interval, and so on. Galileo himself adopted this method of description, but he reached a different conclusion on how the distance increased. Instead of increasing as the integers, Galileo's theory was that in successive intervals of time, the distances should follow the odd numbers, falling 1 unit of distance in the first time interval, 3 units of distance in the second interval, 5 units of distance in the third interval, and so on. In other words, according to Galileo, the distance fallen is proportional to the odd numbers. Galileo reached his conclusions after a brilliant series of experiments in which he timed the ball as it rolled down steeper and steeper inclines, moving closer and closer to the vertical path of a free falling body. Galileo's law of odd numbers can be seen in action in a very unlikely place. At Magic Mountain Amusement Park in Southern California, customers gladly pay for the privilege of plummeting through space under the influence of gravity. Actually, that part of the ride is free.
I don't think I want to do this. Oh, no.
What the customers have really paid for is an arrangement that allows them to survive. At any rate, what about Galileo? If this is 1 unit of distance, this should be 3. This should be 5, and so on, which is exactly what they are. Galileo was right. In successive intervals of time, the distances fallen do follow the odd numbers. But there's something else going on here that Galileo understood perfectly. Notice the total distance fallen at each point. After the first time interval, 1 unit of distance. After the second interval, 4 units of distance. After the third interval, 9 units. After the fourth, 16 units. In other words, at the end of each interval, the total distance fallen is 1, 4, 9, 16, 25, and so on. And those numbers, of course, are the perfect squares. So the distance fallen is proportional to the square of time. At this point, even the most petrified free fall rider can depend on us to tell her exactly how far she has fallen at each instant during the plunge. But the more discerning rider may also want to know how fast she's fallen. Her speed is the distance she falls divided by the time it takes. For example, since she falls 64 feet during the first 2 seconds, her average speed must be 32 feet per second. But that's only her average speed during the first 2 seconds. At the beginning, she was standing still. And at the end of 2 seconds, she was falling much faster than 32 feet per second. Obviously, what this woman really wants to know is not her average speed, but her exact or instantaneous speed at any given time.
Oh, I'm fine.
Her instantaneous speed, which we call v, is proportional to time. First, we found that the distance S keeps increasing since it depends on time. If t changes, s changes. The speed, v, also keeps increasing with time. Acceleration a doesn't depend on time at all. Regardless of the value of t, the acceleration is always the same. On the Earth, the acceleration of a falling object in a vacuum is equal to 9.8 meters per second squared. Because the acceleration due to gravity is so important, it has its own symbol, a small g. According to the law of falling bodies, a body falls with constant acceleration, with speed proportional to time, and falls a distance proportional to the square of time. Discovering the relationships between constant acceleration, speed, and distance was quite an impressive achievement by Galileo. But are we satisfied? What is the nature of this phenomenon called gravity? That question has turned out to be one of the deepest in all the history of physics. To understand why Galileo's relationships are true, and to discover the nature of gravity itself, we must turn to Albert Einstein. Centuries later, this was the starting point from which he built his celebrated general theory of relativity. Unlike Galileo, who spent the last 8 years of his life under house arrest for offending the ruling church authorities, Einstein became a folk hero to a whole world who never pretended to understand what he had done or why he deserved honor. According to the law of falling bodies, a body falls with constant acceleration at a speed proportional to time and falls a distance proportional to the square of time.